Should I wait for people to come in? Yeah, many thanks to the organizers for putting up this wonderful workshop. It's a great pleasure to be here talking to you about the resource theory of quantum channels and the universal role of resource erasure here to you. It's also great to see that there are already many very relevant talks featured at this workshop. In particular, yesterday there was this smooth max information by Kuhn and thermodynamic processes by Felipe. And also, of course, the wonderful introduction to the resource theory approach by Gerardo just now. I'll try my best to refer to these talks during my talk, so that you will be understanding what's going on better. This is the outline of today's talk. I will spend a bit more time on this beyond I.I.D. One-shot result, which is the universal role of log robustness as the one-shot resource erasure cost of channels. Other than that, I will discuss a general framework for channel resource theories, the axiomatic approach of quantifying channel resources, and some open problems. So let me start with a bit of introduction to quantum resource theory. Part of this is already covered by Gerardo's talk just now. So resource theory is a very successful paradigm for understanding many key features of quantum theory and quantum information. It is a particularly interesting and powerful tool in the sense that it's a general framework that can apply to many different specific resources, such as entanglement, coherence, magic, asymmetry, thermodynamics, non-Gaussianity, that you've already heard about a lot in this workshop. So the traditional resource theory approach, which applies mostly to states, which was introduced by Gerardo just now, the objects of state resource theories are quantum states or density operators. And to establish a state resource theory, you also need to define a set of free operations, such as LCC, which gives you entanglement. So that will lead you to some notions such as resource monotones and resource conversion rates. So you can discuss them with these elements. So the completely abstract structure of resource theories are already, like we know, it's the monoidal category where the objects are resources and the morphism are transformations. So in this diagram, the y-axis is the abstractness. So at the very bottom, we have the quantum state, the state resource theories, where the objects are very solid. We have a lot of very solid tools and results to study those theories. And all the way above, we know the very abstract structure of resource theories, which is category theory, or you can even formalize the theory in terms of like GPD objects. So in this talk, we're going to focus on a particularly interesting middle ground where the objects are quantum channels, which is in some sense more general than the theory of quantum states, but more solid than the category theory structure. Here I'll give you some most important motivations why we think the resource theory for quantum channels, or CP maps, are particularly important and interesting resource theory objects. So first of all, in many scenarios, quantum channels or processes are natural and fundamental resources. For example, you use quantum channels to do communication, or you use thermodynamic processes to do work. So that the study in this track will be of practical interest and directly useful. Also, let's look back at the state resource theory. Like many state resource theories are already channel driven. For example, the LCC theory, like the most natural entanglement theory, is given essentially by the definition of LCC. There we can think that the definition of free operations are more fundamental in some sense. Also, we can define some resource theory without free states. So in this case, also the free channels, free operations are in some sense more fundamental things. Also, the results are going to be relevant to the huge body of previous knowledge on like channel capacities and quantum codes. And also, the channels are more solid and modest than the category theory formulation. so that we can obtain explicit results by, for example, lifting from the state theory or some other tools. And another important thing is that the resource theory approach of channels are, from a purely mathematical point of view, it can be non-trivial and very, very interesting. It gives you a different paradigm of resource theories due to several fundamental subtleties which don't really show up in state theories, such as composition issue or partial trace, which I'll explain later. Also, channels can be non-ordinary GPT objects, and we might need some fundamentally different tools to analyze channel theory. So in this work, we are going to address the key aspects of a general framework. Here, general meaning that we don't really specify the resource. We don't require it to be entanglement or thermodynamic processes at the moment. This work will address a general framework with some results based only on the definition of free channels to set the stage and initiate the systematic study of channel resource theories. So first, we'll start with a fundamental framework. So here we discuss some of the axioms that the free resources need to satisfy. Like, you can think of this in parallel to the postulates in state theories that Gerardo just introduced. So first, we require these. We require the set of free channels to be closed under composition, and we need to require the identity map is free, which means that the set forms a monoid. Also, we need the set of free operations to be closed under tensoring. So this also says that tensoring the identity map will be axiomatically free, and also we need the set to be topologically closed. Why say that? We also, like, in our results, we also need some other useful assumptions, such as the permutation is free, the partial trace is free, and sometimes we need convexity. And here we already see some fundamental differences between the state theory. So why do we, for example, need to axiomatically require that the tensoring the identity is free? So in state theory, this isn't necessarily axiomatically required, because we can just define tensoring the identity as a free map, as a free operation. But here, we don't really have that. We don't really have the notion of tensoring an identity map for channels. So this needs to be axiomatically required. Also, the partial trace can be tricky. It's not directly well defined for channels. Okay, here we briefly introduce the definition of resource conversion in terms of channel simulation with free pre and post processings, which means encoding and decoding operations, which are free. So let's look at this single copy, single round protocol. So we say that the channel psi epsilon simulates the channel psi if there exists these free encoding and decoding that satisfy this approximation condition. It's pretty intuitive. This can also be formalized in terms of in the language of free supermap, which you can refer to an upcoming relevant work by Glagor. So we also need to discuss the many copies protocols, since, like, for example, when we are trying to discuss the conversion rates, we need this many copy or composition notion of channels, where we immediately run into problems. So, for example, we can ask, like, how do we consume multiple copies of channels? We have different options. We can talk about the tensor product of channels, which means that you act the channel in parallel. This kind of method is already featured by Kuhn and Felipe's talk yesterday. And we can also run the protocol iteratively, which means that you can do some adaptive intermediate free processings in the middle, so the structure forms a big cone. So this method was discussed in the context of coherence by a recent paper. Okay, also you can ask, like, what does it mean by simulating or outputting multiple copies of channels? This is an important subtlety that doesn't really show up in the state theory. And this will lead to different definitions of resource conversions. I'll not go into too much detail about the results of resource conversions here, but you can recall some relevant results from yesterday's talks. Okay, so the theme of resource theory is the quantification of resource. There are two tracks of studying this. So first is the axiomatic approach, where we focus on the mathematical properties that a proper measure should satisfy, such as the faithfulness and monotonicity. And the second one is the operational approach, where we care about the operational meaning of certain measures. You relate certain resource measures to the performance of meaningful operational tasks. So first, we briefly discuss the axiomatic approach of quantifying channel resources. We need some conditions for valid channel resource measures on channels. So first, we call a resource measure weakly faithful if for all free states the measure vanishes, and of course it is called faithful if the other direction also holds. And the monotonicity condition needs a little bit of modification compared to states. So now we want the resource measure of channels to be non-increasing under composition with free channels. And the composition can be right or left, like it can be pre or post processing. And we also need tensoring a free channel to be monotone. This will make the simulation protocol tensoring identity making more sense. So the mathematical definitions are on the screen. Sometimes we also want it to be convex. So these are the general conditions that we really need for this theory. And we can consider like how do you define monotones in a general way. So first type of general channel monotone is the generating power lifted from state monotones, which can be defined like these. So the first line, we only apply the channels, and the intuition for this measure is the amount of resource measured by a state monotone that you can increase by this channel. And sometimes we also need the complete version, where we also maximize over an extended space. And also this soup can be taken over free states or all states, which like they can lead to different things. So these are the most general definitions. So these quantities have already been studied in many contexts, like entanglement, coherence, Gaussianity. So here we give you a few examples with operational meaning. So in coherence theory, you know that if we take the state monotone to be the relative entropy of coherence, we know from that recent work by Andreas and friends that this measure optimized the second line optimized over the extended space will be corresponding to the coherence generating capacity by an iterative protocol. And also we heard from yesterday that in the context of thermodynamics, we take the state monotone to be free energy, and this will correspond to the so-called thermodynamic capacity. The properties of this class of measures it can be very easily proven that the required conditions hold, especially like when the set of free operations forms a maximal set of free operations in the sense that it is the set of free operations in some theory that is non-generating. Then it can also be faithful, which means that the other direction is also true. But in other cases, it is weakly faithful in the sense that we only have the free operations, the measure for free operations vanish. And the second very intuitive definition is the distance type measure, where we simply measure the minimum distance of a channel to the set of free channels. Here we can also do the maximizing, the complete version. Some example with operational meaning. So here we particularly care about the generalized max relative entropy of channels, which we will define more explicitly later. So one result of this work is that it corresponds to the one-shot erasure cost, which you will see later. And also from Kuhn's talk yesterday, we see that when the set of free operations is a set of constant channels, then it corresponds to the one-shot non-signaling assisted simulation cost. So for this type of measure, faithfulness and monotonicity both hold. It's also pretty straightforward to prove, as you can inspect. Okay, now we'll go into the main result that I want to introduce in a bit more detail today. Is the resource erasure cost. So the question here is that one way to measure the resource content of a channel is like you can think about the amount of noise or randomness needed to erase the resource. So the more rigorous definition is like this. So what do you allow in this resource destruction protocol? You allow attaching a free ancilla, some free channel, and you allow doing some reversible and ensemble of reversible pre and post processings, which is represented by unitary conjugations. So if there exists such a protocol, satisfying that there exists some free channel M, such that there exists a protocol which approximates this free channel, then we say that this protocol is an epsilon resource destruction protocol. And then the minimum random bit log k such that an epsilon resource destruction process exists is called the epsilon resource destruction cost here. So before going to the results, let's define some generalized quantities for channels. So this quantity was already featured yesterday as the generalized max relative entropy between channels. So this is defined by the log of the minimum positive constant such that the channel n is smaller than lambda times m, where it means that lambda m minus n is Cp. It also can take this form. So based on so we can also define very analogously to the state theory the resource robustness, which basically is the minimum portion of some other channels, such that by mixing these channels you can bring it to a free one. So the log robustness is defined like this. And it will collapse to the distance of your channel to the set of free channels measured by the relative entropy, max relative entropy defined above. So the smoothing is given by the minimization over the epsilon bar given by the diamond norm. There are convex optimization problems. And for more general objects, which we'll not really discuss in detail today, they are similarly defined. As long as there's a notion of positivity there, you can define such kind of thing. So the result for the resource erasure cost is like this. This result tells you that the resource erasure cost defined 2 minutes earlier is roughly, very roughly corresponds to the log robustness of this channel. There's a lower bound and upper bound. So the intuition of proving these bounds are quite simply described. The upper bound, which is the achievability, is based on an abstract version of the convex split lemma, which we'll introduce in a minute. And the lower bound, the optimality, relies on the continuity of the isometric dilation and a generalized Ullmann's theorem. So the state version of this erasure cost result is given by this paper, Anurag, Minshu, and Rahul. Here we discussed the generalized convex split lemma. So here we need a base norm. Now you can just think of it as the diamond norm in a channel context. And this is the convex split lemma written in the form of channels. So let n and m be two channels that satisfy this inequality. And we define an average state which basically describes randomizing over permuting the n channel into different slots of M channels. And then this averaging state will be close to the M tensor N state. In particular, we have this, which will directly use in bounding the erasure cost later. So we want to note that this result actually extends to more general cases. It extends to order vector spaces, or you can describe it in the language of cones or extended GPTs. But here we won't go into too much detail about that. This generalized the state version of the convex split lemma by an earlier paper of Anurag and Rahul. So the intuition of the convex split lemma we prove here is pretty simple. So here it's also quite natural to think of it in a resource theoretic way. So here we have a different thing. We have a resourceful thing, and what we do is that we randomize over permuting this thing to the free slots. And what we get is that as long as we have sufficiently many free slots, then the outcome will be quite close to everything is free. As long as we have sufficiently many free slots, that's the point. Okay.
I have a question. Does this hold for any norm, or do you need particular requirements for the norm?
Yeah, we need the norm to satisfy something like it's bounded for states, like it's.
Okay.
Yeah. So the sketch of the proof is like this. It's, sorry? Oh, okay. So by the definition, sorry. Here beta and alpha, like it just corresponds to M and N for channels. Here, yeah, the proof was originally written in terms of more general stuff, more general objects. So by the assumption, we can write beta as this. And then we can directly express the states in this form, and we can then express their distance by the sum of some Bernoulli variables, and then we can just use the variance and properties to bound the difference. So the intuition for this is also that as long as the n is sufficiently large, this will be made small. Okay, so with this generalized convex split lemma, we are able to prove the upper bound on the resource erasure cost right now. So here let's take F naught to be the optimal free channel that achieves the log robustness here, and we consider this very simple resource destruction process where the free catalyst is just a bunch of F naughts, and the unitary conjugations, the reversible processings are just permuting the first law and the ith law. It works the same way as in the lemma, convex split lemma. And then we have this output states, and the convex split lemma directly allows us to bound the difference as long as this n is sufficiently large. So in some sense, the upper bound is directly implied by the convex split lemma. And also, we need to prove a lower bound, which is the optimality. The sketch of the proof is like this. So now we need to consider any epsilon resource destruction protocol. So as by definition, that will be epsilon close to some m in the set of free channels, and then by some inequalities, we can relate it to the completely bounded purified distance, which is also like in this purified distance is also close. We need to do this because we need to employ the general Woolman's theorem to for the completely bounded fidelity, which. Yeah, the completely bounded purified distance is directly given by the fidelity. And then we do the isometric dilation, and by that Woolman theorem, we can see that we can know that there exists such a dilation that is close to the dilation of this. And then what we do is that we what we do in this last step is that we roughly reverse this process on both sides, and the n tensor f thing here is what we want to analyze, and this will be close to this thing, which we can directly express the inequalities and bound its robustness, and then we can bound the delta smooth robustness of this target thing. Notice that this particular bound uses the convexity of the set of free operations, but it is also possible to set a slightly weaker bound without the requirement of convexity. And also, when we discuss the theory in a more general way, we do a slightly different we define a slightly different resource destruction process. We can also obtain a slightly bizarre lower bound where the smoothing is actually on the second argument. But yeah. Okay, so the result we introduced is a one-shot result. So now let's ask the natural question of what is the asymptotic I.I.D. limit of the erasure cost or the log robustness of channels. So by fixing the free channel, this reduces to the familiar problem of the channel QAEP problem that you already heard yesterday. So for states, we have a lot of QAEP results. For example, the quantum Stein's lemma by Nilanjana. So this form, you've already seen yesterday. The I.I.D. limit of the max relative entropy of many copies of rho and sigma will reduce to the relative entropy. So the question here is that if we study the same limit as on the left-hand side for two channels, what does this reduce to? Does it still take some relative entropy form? So by Kuhn's talk yesterday, we know that there's a result of the AEP for smooth max information, which implies this inequality for constant channels. That's a partial result of this general problem. So here it is pretty straightforward to prove this lower bound expressed in terms of what we call right now the channel relative entropy. So the proof is quite simple. It's just a reduction to the Stein's lemma for states. Now the question is that do we have a general upper bound of this? So we know from yesterday that for constant channel, this upper bound will follow from the additivity, but in general, maybe the additivity of this quantity will not hold. So the question is now, like, does it converge to some regularization of this quantity? This problem, I think, is still open right now. So yeah, maybe we should talk more about that. We should think more about that. So in the restore theory context, we now minimize over the free stuff here, which lead to quantities like log robustness. So it's like a different question. It might lead to an easier version of the upper bound problem. For example, we can also ask that does the log robustness, the asymptotic one, the asymptotic version, reduce to some generating power kind of thing? So in the context of thermodynamical processes, I remember that yesterday we had a relevant result, but the restore theory for thermodynamics is a little special. We only have Gibbs state as the free state. Like it might has some special structure that allows some special properties. Like we also recall from yesterday that the theory is reversible there. Okay, so I'll go into some summaries. This work is a framework of restore theories based only on free channels. So we introduced some axioms of the framework of this theory, and we defined some resource resource conversion in terms of a free channel simulation. And we discussed the axiomatic quantification of channel resource We define the variant of the monotonicity and some general types of monotones. And in the last, we introduced an operational beyond I.I.D. result, which is the one-shot catalytic erasure cost given by the log robustness of channels. This result is based on a very general convex slit lemma. The outlook here, actually, there can be a lot to say, but yeah, I'll try. So, of course, we want to make progress on the asymptotic problems, the asymptotic robustness or channel Stein's lemma. And it is also a very interesting question of the asymptotic reversibility of channel resort theory. So for thermodynamics, the theory we heard about yesterday, the reversibility holds. But for some different theories, like this is still open. For example, I want to comment a bit on this coherence theory, where the discussions of the reversibility is also briefly featured in this recent paper. So there we discuss the reversibility in terms of comparing the simulation cost and generating capacity, where generating capacity basically means that the size of maximally coherent state that you can generate. The simulation cost means that the minimum size of maximally coherent state that you need to use to implement some channel. So there, we already know the asymptotic result for the generating capacity in that earlier paper that I mentioned. This gives you the generating power in terms of relative entropy. But the simulation cost is given in this recent paper, which is also some max relative entropy kind of stuff. If you take the asymptotic limit there, it is not clear at all whether these two quantities will hold. So like both reversibility and irreversibility is possible to hold. And another important thing is that the set of operations considered in the results I mentioned is the so-called maximally incoherent operation, the MIO, which is the maximal. So we heard from the last talk that as long as you allow the maximal set of free operations in state theory, we get reversibility, right, asymptotically. But here in the channels, this is still open, like whether this reversibility will still hold. So this is a particularly interesting question to me. And also we need to study more on the resource conversion by channel simulation. There are many other questions that we can ask. For example, the conditions for single copy transformations, maybe in analogy to majorization in entanglement or coherence theory. And also, can we say something about the general rates there? We already heard about some results in this direction in specific resort theories in this workshop, constant channels, thermodynamic processes. And the last thing is that we will want to apply the general framework to specific resources in a more systematic way. So that is also the hope of this work. Yeah, I think the time is roughly okay. So the paper is not posted yet, but we believe that it will be on archive soon. Thank you so much for your attention.
Yeah, questions? Yeah.
Just made some comment on smoothing.
Oh, thank you. Yeah.
Consider the second slot. Can you say what I missed that? What does that yield, and why is that relevant or interesting?
I'm not sure. So you're talking about this, right? This is actually not what I want to emphasize here, but the result is that so now we are not following the definition of cost for channels. Like we just ask about very general objects. So the destruction protocol is we allow here is any arbitrary permutation into the free slots and an ensemble of doing this, randomizing over this. So it's a slightly different definition than the rigorous one we gave before. And there, it is pretty weird that we can prove this kind of lower bound, where the smoothing is so the smoothing is defined in terms of optimizing over the epsilon bar of the second thing. So It's quite bizarre, but we didn't really look into that in too much detail. Yeah.
Yeah.
So this convex split lemma for that you have for channels. So I believe this in particular works also for all general probabilistic theories, right? For all cones, right? So you get this in terms of the base norm, right? The proof
Right.
I think goes through
Right.
because you just use properties of the base norm and that's it.
Yes.
Can you turn the slide back to this relative entropy expression for two channels? EMN, what's more at the end?
Here, right?
No, further at the end, this
Oh.
relative entropy.
I see, I see.
I don't remember the exact name.
Here.
Right, this one, right.
Okay.
Do you have some additivity result for that monster?
No.
I think this should be true.
Okay.
Well, do you think
Thank
it should
you.
be false?
You think it's okay, that's good, then at least we have something to discuss.
Okay, we still have time for questions.
Yeah, sure.
So I have one question. So
I'll modify
in
it
this
already.
paper by Fernando, right, where they consider reversibility of the rates for resources, going from rho to sigma, they consider free operations which are apparently free only in the limit of something, right?
Right. That's the limit. Yeah.
Yeah. So is it also possible to consider operations which are, free for finite, and do these conversions? Like for example, the resource destruction, the operations are free for finite n, right?
Right.
Remain
So,
free.
so are you asking about the reversibility
Yeah,
for
the
states,
reverse-
for
yeah.
state theory?
Apostate theory, yeah.
I'm
Have
not.
you looked into that question at all, or?
No. So this is not the concern of this work.
Yeah.
But I think the reversibility proof there requires the asymptotic kind of
Yeah,
thing. I'm
yeah,
not
exactly.
particularly sure about the
Right.
the finite
Yeah.
copy thing.
Okay.
So for your one-shot bound of the erasure cost, is the lower bound, the epsilon term can be improved instead of writing at the square root of that. Can you write it as a linear with respect to epsilon?
It depends on the form of the inequality. So here, this is what we get. Andreas, do you have comment on this?
Well, maybe it's just an artifact of the proof. I mean, maybe there's a better way of proving it. You would have to look at Anurag and Rahul's paper. I thought that you have similar things.
Yeah, I'll have to double check whether the square root is there or not.
No, maybe not. Yeah, actually, sorry. I think, but they say that's because they can deal with purified distance, and then you don't have this. This is because we have to go to we have to switch between fidelity and tracing, and that's because of the form of the convex split lemma. The state one, you have a better version where you can talk about purified distance.
Ah.
I think maybe you can avoid it. But okay, who knows? Maybe it can be avoided also.
Oh, so here at some place you have to switch between fidelity and L1.
Yeah, because our convex split lemma only, like, the proof is directly in terms of the norm. There's no master version, right?
It's not in terms of
your
D.
work, you come from relative entropy, and then you can prove a bound and purified, and then ultimately, if you want, you can go to trace distance. But we don't have this kind of option. We have only the norm version.
I see. Yeah, so I see that the proof is kind of more similar to the older one, right? I mean, in terms of trying to use some concentration bounds and so on.
Yeah. It's just
Yeah.
Championship.
Okay. All right. So yeah. Any more questions? Okay, so let's thank.
Thank you.